Okay, questions? No, I'll come back and get them.
Can you go over J on the part 1? J.
Okay, so that's an alkyne with camel and acid. So what we're going to do is, for alkynes, we're just going to react, whenever we react it with CamNO4, it's always going to cleave. So we're going to cleave the triple bond, and then we're going to form the carboxylic acid on one side, and then this is a terminal alkyne, so we're going to form the carboxylic acid on the other side, except that carboxylic acid is going to be further oxidized by the CamNO4 to form carbonic acid. And then we know from last semester that carbonic acid is CO2 dissolved in water, and so it will reverse itself and form CO2. So the internal, if it's an internal alkyne, you're going to get 2 carboxylic acids. If it's a terminal alkyne, then this piece will become CO2 in water. Just like last semester, if we did CamNO4 oxidation on basically a terminal alkene, then this part also became CO2 in water when we did its oxidation.
Wait, what did you say about this? So if it's terminal, what happens? If it's internal, what happens? On the right.
Well, if it's terminal, what happens is what I wrote down.
Yeah, but like, what's the difference between all the way at the top right? You have one that has an H and an OH group, and then the other one has an OH and an OH group. Why?
So when we cleave this, we turn each one of these into carboxylic acids. So this one and this one. The problem is this is formic acid, and formic acid can be further oxidized to carbonic acid. So last semester, when we looked at terminal alkenes and we oxidized those with CamNO4, what we found was this part became CO2. Right? Because if we looked at that, what we said was that formed formaldehyde, and then the formaldehyde was oxidized. Well, you can think of it being oxidized first to formic acid, which is the 1 carbon acid, then further oxidized up to CO2, or to carbonic acid, which then gives CO2. So any terminal alkene or alkyne, the terminal part, the terminal end carbon, is going to become CO2 in water. If it's internal, you just get 2 carboxylic acids and you're done. So,
Going from an OH group to a Br, is that considered an oxidation or reduction?
that's the last, or that's the second to last question, right?
Yeah.
So, is that, oh, sorry, wrong one. Well, you know what? No, right one. Our rules about the loss of oxygen, gain of oxygen, loss of hydrogen, gain of hydrogen, they're not as complete as I haven't made them as complete as they should be. One of the things is when you lose an OH, that's replaced by an H. Or when you lose oxygen, it's gained by an H. When you gain oxygen, it's usually replacing an H. So in this case, the only way to know if this is truly oxidation is to look at the oxidation number of this carbon and of that carbon to see if it's changed. So the oxidation number for this carbon would be what? Zero. And the oxidation number for this carbon would be 0. So this is not an oxidation reduction reaction. Because honestly, well, because I've not been completely, technical. If I lost this OH and I replaced it with an H, then it would be an oxidation reduction reaction. This is actually what would be the better classification of this reaction? Kevin? Sort of. It's substitution, because I'm substituting an OH for a Br. So it's a substitution reaction, not oxidation. But if you want to know if it's truly oxidation or reduction, that's why you have to do the oxidation numbers of the carbon. And you only have to look at the carbons that are changing. So these other carbons, hopefully everybody put down their oxidation numbers, but it's not critical if I'm just determining whether it's oxidation or reduction. I'm only looking at the carbon that are being changed. So yeah, if I replace the OH with an H, it would be reduction.
And then for B, going from an alkyne to having hydrogen, would that be a reduction?
Or maybe neither. So let's look at that. So if we just use gain and lose hydrogen or oxygen, again, for each other, we would say that this carbon here is gaining oxygen, so it's being oxidized, while this carbon right here is gaining hydrogen, so it's being reduced. So we have both processes happening. And so if we looked at the oxidation number for this carbon and for this carbon, it would be 0. And then for the carbonyl carbon, it's -2. And for the CH2, it's that's +2. We in agreement of that? And then what's this one? -2. So I'm going here from 0 to +2. That means that I'm losing electrons, right? So that's oxidation. And then going from 0 to -2, what am I doing? I'm gaining electrons, so now I'm undergoing reduction. So one carbon's oxidized, one carbon's reduced. It's a wash. This isn't really an overall, it's not an oxidation or reduction. And again, well, okay, so every one of these, is that true? No, it's not true. Except for number 1. And letter F is going to require some creativity. Every one of those reactions except A, and I'll classify F. So B, C, D, and E, you actually could give me the reagents necessary to go from reactant to product. And our typical oxidizing reagents are things like KMNO4, oxygen gas, osmium tetroxide, OSO4. Reducing reagents right now are just H2. So this one how would I get from triple bond to ketone? What would I add? Yellow when you got it. H plus H2O. We agree? Okay, so let's deal with the mercury issue. So I'll accept that answer with or without the mercury. So H plus H2O is our hydration, right? We're going to add H plus to one of the two carbons. We're going to add the OH to the other carbon. This is going to add Markovnikov, except the problem is there's no Markovnikov because both carbons have the same number of hydrogens, 0. But that's okay, because this is a symmetrical alkyne. So whether I add the H to the left and the OH to the right or vice versa, I'm going to end up with the carbonyl on carbon 2. So I get the same product either way. Now, a triple bond is more stable than a double bond. And so H plus H2O addition really needs something to kind of give it a little bit of a kick, and that's what the mercury does. So whether you include the mercury in the H plus H2O addition, I wouldn't take off points either way. But if we're going to do this, the reaction would go a lot faster if I had mercury in it, because the mercury is going to activate the triple bond. It's going to act as a catalyst. And we could probably go back to last semester and remember that the mercury, now the mercury is not going to add it's going to be mercury 2 plus, but it's not actually going to physically add to either carbon, but it's probably going to sit on the triple bond and make the other two carbons a little bit more electrophilic so that they can react faster. So that's not an oxidation. Those reagents are not oxidation reduction.
So is it neither?
So it's neither. Yeah, so it's neither. Neither was an option. Sarah?
Could you go over the reaction for E in part 2?
For E in part 2. Okay. So in E in part 2, we're going to take a cyclopentyl. We're going to add a cyclopentyl group to the triple bond, and what we'd like to do is we would like to convert the alkyne into an aldehyde. So in our overall thinking then, what do we need to add to the triple bond to make a carbonyl? It's the same reagent that we just used. We need to add like an H and an OH. Right? That's the net result. Because when we add H and OH to a triple bond, the OH attached to the double bond, the enol, then becomes a carbonyl by tautomerization. But in this case, I don't want to do it Markovnikov. I want to do it anti-Markovnikov. I would like to add the H here and the OH to the terminal carbon. So then I have to think of how do I add H-OH anti-Markovnikov? What reagent should I use? No, there's no H2O2 in that one. How did we do it with alkenes? It's not on your chart? Oh, did I rule out? Sorry, there was peroxide there. But it's not the most important thing. The most important thing is the boron. So yes, there would be H2O2. This, what we would have used last semester was, instead of SiA2BH, we would have used BH3. So last semester we used BH3 and H2O2. I would accept that reagent, but the difficulty here is that because the triple bond is linear, there's not a lot of steric hindrance because the BH3 is small. Remember, we want the BH3 to add to the less sterically hindered carbon. And a triple bond, since it's linear, doesn't have a lot of steric difference between those two. So the boron could actually add to both carbons. It probably would add more to the end carbon than in the middle. But if we want to make sure that it goes 100%, I can't add any more steric hindrance to a triple bond. So then, I break open my organic chemistry toolkit. And the first thing it says is, if you can't make the reagent the reactant more sterically hindered, make the reagent more sterically hindered. And so that's what we do by using the secondary isoamyl borohydride. And so now it's sterically hindered and forces it to now add to the end carbon. So once that happens, we end up with our enol, and once we have this enol, it's now going to tautomerize so that this OH group can form an aldehyde. So like I said, I would accept BH3, H2O2, but in reality, the better reagent would be sterically bulky. What else?
On page 1C.
One C. Okay, so we're going to do two reactions, and we're going to do those sequentially. So if I take, they were all the same alkyne. So I'll take my butine, and I'm going to add HBr to it. All right, so what am I adding to the triple bond?
Josh Hughes.
The first step,
What am I adding to the triple bond?
you're adding an HBr.
I'm adding an HBr. Should have jumped on that one. So I'm going to add an HBr. How am I adding it? Markovnikov, anti-Markovnikov. Markovnikov. Are you sick and tired of hearing me say that? Then think it and say it. Because I am too. But that's what we got to do. Right? We got to have our reactions down so that we can remember that. Okay, HBr Markovnikov. Now I'm going to add HBr to that with peroxide. So what's that going to add to the double bond now? And no, we're not to whether it's Markovnikov or anti-Markovnikov. What are we adding? HBr. How? anti-Markovnikov. So now I'm going to add HBr anti-Markovnikov. So that means that the Br is going to go here and the H is going to go there. So now I've got the Br here, I've got the H here, I've got two H's and a Br. So if I break those two steps down and add HBr Markovnikov, then anti-Markovnikov, or vice versa, what kind of dibromide did I make? Well, there's actually no stereochemistry in this reaction. So I'm looking for something that starts with a V, of vicinal, or you could say 1,2. Right, so this makes a vicinal dibromide. That goes back to last week. Vicinal, vinyl. So that makes a vicinal dibromide. Of course, that's a way to make a vicinal dibromide in 2 steps. How would I go from triple bond to that molecule in 1 step? So if I said, what's the reagent to go from the triple bond to the 1,2 dibromo compound, what reagent would you use? Kind of a trick question, because we can't go there in 1 step. Because if somebody said, well, we can do it with Br2, Br2 leaves a double bond behind it. So we can't do it with Br2. We've got to do, if we want to make a vicinal dibromide, we have no choice, 2 steps. And wasn't there one of those on the, just a hint, B in part 2? It's the same problem. Right, because if it was Br2, it would leave the double bond behind. I glossed over that. So we have to just be careful that we make sure that we don't think that a double bond is a single bond or vice versa. So this is the way to make vicinal dibromides, is to do 1 Markovnikov, 1 anti-Markovnikov. Doesn't matter whether you do which way you do it, you just have to do 1 of each.
So there are 2 possible ways that you could do B.
2 possible ways that you could do B. There's 2 possible ways that you could do this one, which is the same thing. You want to propose one?
Well, we did. You could possibly do 2 equivalents of HBr and ROOH, or you can do an HBr reaction and then an HBr ROOH.
Well, I like the HBr and then the HBr ROOH because that's what we've been doing. I'm not sure that I like your 2 HBRs with each having ROOH, if that's what you said.
Is that not an option?
That is not an option in my book. So let's figure out why. So if I decide to add 2 HBRs with peroxide present, I'm going to add 2 equivalents of HBr, right? Markovnikov, anti-Markovnikov. I'm going to add anti-Markovnikov, so that means that I'm going to add an H and a Br with the double bond, and then the second H and the Br, and so I'm going to make a geminal dibromide on the end carbon. So if you want to make a geminal dibromide on the least substituted carbon, do 2 anti-Markovnikov additions. So that's what I don't like about that one. So we really have to do 1 of each. We don't have a choice.
I didn't know when, the double bond to O.
Oh, with the, well, it'll always occur. Yeah, whenever we have an OH attached to the double bond, whenever we have an enol, all of the enols that we're going to make are unstable, and so they will all tautomerize to form the ketone or the carbonyl. They will always do that. Because all the enols we're making are simple and they're not stable. So every time you do H plus H2O to an alkyne, you're going to make the carbonyl. The question is, are you going to make the ketone? Or if it's terminal, are you going to make the aldehyde? Anything else? So last time we did what? We did Grignards. So then I brought these in-class problems. That hopefully were part of the video for today. There is no video for Monday because we're going to talk about epoxide opening. That should be a lot of review, but we'll see. So it's just the spillage factor is all that's. Yeah, I know. That's the only thing I cringe about when I hear that is. Okay. So do we know how to do all those? How about A? Which one were you going to ask?
I think so.
From last time? Oh. Sure, you can ask me about that if I know which one I'm looking for. You might have to hold it up so I can see it. Which one?
It's just a primary alcohol, and it reacts with H+.
So is it like this one? Read the structure to me. Is it a cyclohexane ring?
Yeah.
With what on it?
With,
Oh. Okay, got it.
I was just wondering why it doesn't do no reaction to the H2O.
So we got OH minus, we have H2O, and then we have H2O without rearrangement and with rearrangement. There you go. Thanks. Normally I would have all those with me, but again, my organization ended last week, right? It ended very quickly. Okay, so the question is, if I try and react the primary alkyl halide with H2O without rearrangement, will I get a reaction?
So that one I knew was no reaction. Like for the one with the
Okay, so the rearrangement. Okay, so with rearrangement, we have to think about how to rearrange it. And that sounds kind of like, yeah, of course. But normally when we do rearrangements, what happens? Our bromine leaves, we end up with a carbocation, and then we rearrange. Am I allowed to do that in this molecule? No. So there's got to be an alternative method to rearranging this for primaries. And here's what happens. What happens is that I can't form a carbocation. So the hydrogen is going to slide over and migrate, and then the bromine is going to leave at the same time. So when that happens, I avoid the primary carbocation. As a matter of fact, if I was to write the transition state for that, I would bridge the hydrogen in between the two carbons, and there's going to be a slight positive charge on the second carbon as the hydrogen slides over, because my final product of that rearrangement is going to have a positive charge there. So it just means we need another mechanism for primaries. And so we do the rearrangement and the leaving group gets kicked off all at the same time. Normally, we would just have the leaving group leave, get a carbocation, and then do the switch. And that's what happens with secondaries and tertiaries. But with primaries, we just need this little extra step. Flush. And so that's something we need to remember from last semester. So that's how the primary systems work. So if water was to react with that molecule, it would have to do a rearrangement, because water's not strong enough to kick off a leaving group. Which is why if you want to replace the Br with the OH, you have to use OH minus. You have no choice. Bless you. Okay. How is for the in-class problems from today? I basically chose reacting Grignards now with esters and what are called acid chlorides and epoxides, which I'll probably come back to on Monday. But what's different about adding the Grignard to an ester than adding a Grignard to just a normal carbonyl, an aldehyde, or a ketone? Or adding it to a C double bond O Cl. Did you pick that up from the video, book, whatever you looked at ahead of time?
You need two equivalents of the
Well, I need two equivalents of the Grignard. So the final product that I'm going to make has what? If this is, let's call this R in a box.
gonna have, like, there's gonna be three groups attached to a carbon, two of them are gonna come from
and 2 of them will be. So if I have the R in the box as the Grignard, then the final alcohol that I make is going to have, let's call this R in a circle. So the final product that I'm going to make has 2 R groups from the Grignard, and then the 1 R group from the ester, or the 1 R group from the acid chloride. So this is a great way of making an alcohol where 2 of the R groups are the same, because they're both coming from the Grignard. Did everybody kind of pick up, or did the mechanism of how that happens make sense? I'm not getting any yeses or nos. And a no's perfectly legitimate. But still nobody wants to say no. All right, I'm confused. So talk me through it. I'm going to replace OR. No, let's do a CL first. That's easy. Okay, what happens in the first step of the mechanism? Okay. So the Grignard attacks the carbonyl, and the pair of electrons goes back up here. And I make that compound. Why? Yes, that's actually correct. So first step is the same as all Grignards. Have the Grignard react with the carbonyl. Now, whenever we do that step, the molecule will always kind of take a time. I'm going to give it personal characteristics. It's going to take a time out and say, can I reform my carbonyl? And so it can reform the carbonyl if it can bring this pair of electrons down, but something's got to leave. And so if something can leave, it will do this because a carbonyl group is very stable. So we would like to reform the carbonyl every time it has something added to it. Think about what we did on Wednesday. What we were doing on Wednesday was we were adding our Grignards to functional groups that were either aldehydes or ketones. And so when the Grignard comes in and attacks the carbonyl, we were forming the O-. And even though I didn't say it at the time, the molecule stops and it tries to reform the carbonyl. So it wants to bring its pair of electrons back down. But the problem is, there's either an R and an H attached here, there's an R there from the Grignard, and there's an R and an H over here. Well, time for some review. What makes a good leaving group? Weak bases. So leaving group abilities based on basicity inversely. So a great leaving group is a lousy base. What's our strongest bases? What kind of minus? C minus. So a C minus is our strongest base. Comparable to that is H minus. So these guys aren't leaving, that's not leaving, that's not leaving. So then the molecule's like, okay, I just hang out and wait for an H plus to come by, and get protonated. When you use what we're going to later on call carboxylic acid derivatives, the OR or the Cl are potential leaving groups. Now you might say OR minus, not a great leaving group. Not the question. Could it be a leaving group? And the answer is yes. So with these as possible leaving groups, when you form the O minus, it can come back down and it can kick that group off. And so what does it form? It forms a ketone. And then what happens? Well, if I tried to do this in a 1-to-1 mole ratio, the first time this happened, there'd be an R minus hanging around, and then the R minus would come in and add there, and I get a whole mess of products. Simply because the reactions are going to occur at different times. So I can't fight that, so what I'm going to do is make sure I add 2 R groups so that way I form the final product by having the second step. There's more than enough R minus around to do that second step. So the mechanism changed. Because it's not a ketone or aldehyde anymore, it's a carboxylic acid derivative. It has something that can be a leaving group. And so if that's the case, that's what's going to happen. So we require 2 equivalents because we want to just, if it's going to add 2 anyway, add 2 to everything. So that's the second class of Grignards. So that's how you would do A and D and E and F. So that's the other class. That's the other class of compounds you can react with Grignards. Now, as far as the epoxides go, we'll talk on Monday. We'll do a little review. There's no video. I'll live lecture or ask you questions about epoxides. So to date, we only have one way to open up an epoxide, and that's by adding acid to it first. Grignards, of course, if I add acid to the Grignard, I kill it. So I now need to talk about what happens when you react negatively charged nucleophiles with epoxides. And if you have any kind of suspicion about when we do things, we usually do things one way, and then we turn around and we do it the opposite way. So with C minus is going to attack the carbon that is least substituted. And so that's what we need to talk about. Okay, so I'll take your problems, the homework problems from today, and sadly, I've got another set of homework problems for Monday.
Great.
Over Grignards and like NABH4. If you have any questions on those, email me, come see me, or we can talk about those on Monday as well.
The ones on the back, are they just for extra work?
The ones on the back.
They say January 3rd.
Well, I erased the January 23rd and made it January 25th. So the whole thing, I think you can do the whole thing. If not, we'll talk about it on Monday.
So this one, the first one adds here, just like we did in the beginning. And with the second one, add somewhere else.
So what happens is you form this as a ketone,
Right.
and then the second one adds the ketone, so you end up with these 2 groups being added to that carbon. So 2 of the groups are the same on the tertiary alcohol.
So both of these Grignard, right, are attached to this middle.
Yes.
Okay.
Yeah.
So I have 2 of these.
Yep.
Okay. And
So you got
because the
2
OCH
CH2, CH2, CH3 groups.
Right, and the OCH3 leaves to the